Hello everyone. We are looking into different methods of geophysical exploration. Today, let us start looking into seismic methods of subsurface investigation. Right? Seismic methods are based on the propagation of waves in an elastic medium. Right? How the propagation of waves takes place in an elastic medium, that is what we make use of in seismic methods. Actually, the way in which the seismic waves are getting transmitted in different formations, or in other words, simply the velocity of the transmission is different in various rock formations. Right? That means the way in which the seismic velocity travel through the different formation is what is being made use. For example, if you consider this is a block of granite, then you have another block of sand. The way in which the shock waves are going to be transmitted, for example, you are transmitting from this side, the way in which it is going to travel through the sand will be different than that of the way in which the same shock waves are going to travel through granite, isn't it? Which means the velocity is going to be different. Velocity in the case of massive rocks will be considerably higher than that of sand. So, velocity of the shock waves or seismic waves is going to be high in granite, whereas it is going to be low in the case of sand. That is what is actually helping us. This is what we are going to make use of in seismic methods to understand about the subsurface. Right. In the case of seismic methods, the seismic waves are actually artificially produced by us. Right. But seismic waves are also generated during earthquakes, volcanic activities, also landslides. Right. That means a huge mass of earth falls or slides suddenly, that also triggers shock everywhere. Right. So, seismic waves are generated by natural processes such as earthquakes or volcanic activity, volcanic eruption or landslides, and we can also artificially produce seismic waves. Right. These seismic waves, when it gets transmitted through the formation, what happens? Right. Generally, when external forces are applied to a body, the body tries to resist that by some balancing internal forces. Right. That means when we try to pass some shock through this body of granite, obviously internally some forces are developing to resist the transmission of shock waves, or in other words, the force that is trying to disturb the rocks are balanced by internal forces. So, stress is a measure of intensity of the balancing forces. Right? Stress is the measure of the intensity of this balanced internal forces. So, when a body is subjected to stress, right, when it is subjected to stress, it undergoes a change in the shape or size. That is what we refer as strain. Right. So, when the body is subjected to stress, stress is maybe due to the transmission of shock waves. The different particles in the rock mass are disturbed due to these shock waves. Right. Though internally some balancing force gets developed, body may sometimes undergo some change in the shape and size. If it undergoes change in the shape and size, we say the body has got strained. So, stress and strain are related. If the stress is more, body gets very much strained. The relation between stress and strain are very simply stress and strain depend on elastic constants. Okay. What are elastic constants? The elastic properties of the rocks can be described by the elastic constants such as Young's modulus, bulk modulus, shear modulus, Poisson ratio. Right. Why do we call this as elastic properties? Because when the body is subjected to, as we had seen in the previous page, when it is subjected to some stress, the stress may lead to straining of the rock mass, but the strain is restricted to elastic deformation. Right. When the strain is restricted to elastic deformation, the way in which the stress and strain are related is going to be dependent on the elastic constants such as Young's modulus, bulk modulus, shear modulus and Poisson ratio. Let us very briefly run through what they are. Right? I have put up one slide under each. First is the Young's modulus. So, always these elastic constants refer to some ratio. Here in Young's modulus is the ratio of stress strain when the body is subjected to simple tension or compression. Right? Suppose if you consider this body drawn in as a black box, when it is subjected to tension, we try to pull the body on either side, or when we subject this to compression, we apply the force in reverse direction. That means this is what is the compression. So, this is compression, this is tension. So, Young's modulus refers to the relation between or the ratio between longitudinal stress and longitudinal strain. Right. So, the stress applied per unit area divided by unit shortening or lengthening, right, is the force that is applied to this body. So, when this body is subjected to tension or compression, it undergoes some change in the length, right. When you subject to tension, it is the thickness gets reduced. When you subject it to compression, thickness gets increased. Right. So, the ratio between longitudinal stress and longitudinal strain is the Young's modulus, referred usually by letter E. Then, bulk modulus is the stress strain ratio under uniform compressive stress in all the directions. In the previous case, Young's modulus, we were keeping a piece of, let us say, a rock or maybe a concrete block, and we have subjected that to tension or compression, right. Whereas in bulk modulus, we subject the body for uniform compressive stress from all the directions. That means, this is the body which we are considering. Let us consider it is a sphere, and we subject that to uniform compressive stress from all the directions. When you subject this body for uniform compressive stress, the body size gets reduced, as you see here. Previously, the diameter, let us say if it is 10 centimeters, the diameter now gets reduced to 9.5 centimeters. So, this is how the ratio of stress by strain to a body that is subjected to compressive stress is known as bulk modulus. So, bulk modulus K is the volume stress divided by volume strain. Okay. So, this is what is referred as bulk modulus. Then the next is the shear modulus. So, shear modulus refer to stress strain ratio for direct shear, right. So, that is, it is determined as the shearing stress, which is the force tangential to the surface displayed. That means, imagine there is a body of this shape, right. We are subjecting this body to shear. That means, we try to push only the top surface of this body, right. So, the body is now subjected to shear. So, what is shear? Shear force is a force that is operating on opposite direction, right. So, subjected to displaced per shearing strain, which is the displacement referred as this, right. So, this is the displacement along the line of shear force, right. So, shear modulus thus is the relation between shear stress by shear strain, shear stress by shear strain. So, this is what is the rigidity modulus. What is the difference in the case of rigidity modulus? In the case of rigidity modulus, we subject the body to shear. That is what is the major difference. So, we subject the body to shear stress and observe what is the deformation takes place. So, shear stress divided by shear strain is the shear modulus. Then the last is the Poisson ratio. In Poisson ratio, we consider the change in the shape of the body due to the applied force. Okay, it is something like, if a compressive force is applied to a body, right, as in this diagram, if you give compression as indicated by the red arrows, right, the length of the body gets decreased because we are giving compression from either end. So, when we do like that, the size of the body gets reduced, especially the length gets reduced, the width is increasing, length is reducing, right. So, when you subject the body, right, there is a decrease in the length, right, increase in the width. That is what I have indicated. So, the length gets decreased, right, whereas the width got increased, right. Suppose, on the other hand, if you subject this body to tension, that means, if you pull this body on either end, right, when you subject it to tension, what happens? It becomes like this, right. Length is increased, whereas width is decreased, isn't it? That is what is written here, right. So, if the body has a length L, right, if the body's length is L and the width is W, Poisson ratio refers to ratio of transverse strain to longitudinal strain. That means, we just consider how the body has changed its shape. So, what is the change with respect to width? What is the change with respect to L? So, ratio of these two is known as Poisson ratio, right. So, we have seen 4 elastic constants. Why we are looking into elastic constants is because stress strain that is going to be developed during seismic operation is dependent on elastic constants. That is why we had a look into these 4 elastic constants: Young's modulus, bulk modulus, shear modulus and Poisson ratio. Now, after having seen and understood about these elastic constants, let us move on to seismic waves, right. So, what is seismic waves? Though I referred seismic waves, here let us understand what are seismic waves. So, these seismic waves are of acoustic energy. It is something like a shock or vibration. When you are standing on a bridge, when a heavy vehicle moves, when the bus moves, we feel the vibration. So, how do we feel the vibration? This acoustic energy is propagated on the spans of the bridge, on the road over the bridge, right? So, this is an example of a seismic wave. So, seismic waves are waves of acoustic energy. These waves or vibration is generally generated during an earthquake or during an explosion or some other energy source, and they are transmitted or propagated within the earth material. They are transmitted within the earth material, right. The velocity of seismic waves, we have already seen, depend on elastic constants. Very much it depend on the elastic constants and the wavelength, as well as the property of layer or layer thicknesses. That means, if this is the ground surface, how many layers are present below the surface? Maybe this is 1 layer, 2 layer, 3 layer, 4, each one may be of different composition, right. The way in which the shock waves are going to be transmitted through them, through this formation, right, actually, right, this is how the shock waves are traveling in the formation. It depends on the velocity, depend on elastic constants as well as wavelength and the thicknesses of different layers below the surface of the earth. So, there are 3 types of seismic waves, right. The uniqueness of these 3 types of seismic waves is all these 3 types, they travel with different velocities through the earth, right. So, these 3 different types of seismic waves which travel through the earth at different speeds are surface waves, P waves, S waves. Okay. So, what are they? So, first is the surface waves. You can look at the graph here, or graphics or animation here. So, it clearly indicates that in surface waves, it is similar to water waves on the ocean, right. All of us see the waves on the ocean or on a large lake during windy time, right. So, we could see the waves. So, in the same way, you can see the surface waves causes waves on the surface of the earth. So, due to this reason, right, you can see this causes the surface wave cause rolling motion that people can feel, right, especially when you are above the epicenter. What is epicenter? Epicenter is the on the surface. The focus is the point where the earthquake gets generated. The point which is just above that on the surface of the earth is the epicenter. So, when you are on the just above the epicenter on the surface, this is what you will feel. Look at this orange dot, right. Look at this orange dot. This orange dot is actually undergoing rolling motion, right. So, these particles which are going through a circular motion, more or less in elliptical path, right. That is why they are also called as Rayleigh surface wave passes, right. With the axis of rotation perpendicular to the surface. So, perpendicular to the your screen. Now, the axis of rotation along this elliptical path is perpendicular to your screen. Right. What is interesting with regard to surface waves is, though this particular orange dot which you see here, right, is going in a circular or elliptical motion, as the depth increases, the width of the elliptical path also decrease. Right. Here you can see, please notice this particular place, the width of the ellipse got reduced. Somewhere over there it was going like this. Right. So, whereas somewhere here it get reduced, somewhere here further reduced, somewhere here just it goes up and down. Okay. So, depth is important here. So, surface waves are very strong, very close to the surface. That is why during major earthquakes, surface waves cause major disturbance, right? Especially large buildings fail due to the surface waves. So, they cause greater calamity than the other type of waves. So, first we have understood what are surface waves. Then number 2 is the P waves. P waves, the letter P refers to primary. Primary waves generally travel through the interior of the earth, whereas as the term surface says, surface waves are generally limited to shallow subsurface of the earth. Right? They are restricted to shallow depth, whereas the primary waves travel through greater depth. They travel through the interior of the earth. P waves are also called as longitudinal waves because the P wave, if this is the direction of propagation of P wave, the particle along this path are vibrating in this direction, right? That means they vibrate this way, right? The particle vibrate this way. So, that is why it is called as primary waves. They are also called as compressional waves because each particle pushes the other particle. It is something like if we are all standing in a queue along a straight line, if one person leans forward, everybody in front of him will lean forward. If all of them lean backward, all of us will lean backward. Or if one person pushes us behind, then all of us will move backwards. It is something like that, right? So, this is known as compressional waves. So, this is also equivalent to when you have a spring, when the spring is attached to the wall and if you pull and push the spring, it is something like primary waves. Now, let us focus our attention to this animation. Look at all the particles, all the dots, right? They move this way, right? They are vibrating in this manner. At the same time, the wave is getting transmitted along this line. So, you can see this black arrow, that is the direction of wave, right? Each particle pushes the other, that is how the wave is traveling towards the right hand side. From left towards right, the wave is traveling. But how the wave is traveling? Because each black dot pushes the other dot, right? This process is known as compression and rarefaction, right? It means during compression, the dots are very close to each other, right? Whereas during rarefaction, the points are very much away from each other. They are very much away, then they are closer to each other, as you can see, understand from this animation, right. So, these are known as primary waves. Then the third is the secondary waves. Please let us focus our attention to the animation here. As you can see here, the particles are vibrating in this direction, but the shock wave is transmitted from left to right as in the previous case. They are known as secondary waves. Secondary waves are called as transverse waves because the particles vibration are perpendicular to the direction of propagation. So, this is the direction of propagation, but the particles are vibrating in this direction, right. That means up and down, perpendicular to the direction of propagation. So, this is equivalent to, in the previous page we said it is something similar to spring, whereas this is similar to shaking a string up and down. If you attach a string on this wall, right, if you attach a string and if you hold the string somewhere here and if you shake it, it will go up and down, isn't it? So, this is what will happen when you attach a string and shake it from the other end. So, here exactly in the same way the particles are vibrating up and down, but the shock waves are traveling towards the right hand side. So, these waves also travel through interior of the earth. So, first we had seen surface waves, they travel generally at the surface. Then we had seen primary waves, right, or P waves are also called as longitudinal waves. They travel through the interior of the earth. Then we have now seen secondary waves. Secondary waves are called as transverse waves and they also travel through the interior of the earth. Okay. So, these are the three different types of seismic waves, which are three important types of seismic waves. All of them travel in different velocity, right. Now, let us have a look into, focus our attention to the primary and secondary wave. Let us focus our attention one by one. First, let us see this table. Please focus your attention to this table, right. This table has got two columns, one for primary, another one is for the secondary waves, right. So, what is the type of wave? Primary is longitudinal, that means as the wave is transmitted, the particles are vibrating in this manner. Whereas in transverse, the wave is from left to right, but the particles are vibrating up and down. That is why it is called as transverse wave. Now, interesting thing is the velocity. Primary waves are always faster. Secondary waves are slower. Because of compressive nature, primary waves are able to travel faster through the Earth's interior. Secondary waves are slower compared to the primary waves. Now, let us have a look into how we can calculate the velocity. Velocity of primary wave V is equivalent to square root of k plus 0.75 times of n divided by the density. K is the bulk modulus, n is the rigidity modulus. So, primary wave's velocity, as it travels faster, it is controlled by both, or it is dependent on both bulk modulus as well as rigidity modulus. Whereas, in the case of secondary waves, the velocity of secondary waves is considered only are dependent only on shear modulus. So, velocity of the secondary waves depend only on the shear modulus. So, it is very interesting. Because of this reason, the primary waves can travel through solid, secondary waves can also travel through solid. Here, in the case of liquid, primary waves can travel through liquid, whereas the secondary waves cannot travel through liquids, right. Why? That is what is shown here. Secondary waves cannot travel through liquid, as liquid has got no shear or rigidity modulus, right. However, same liquid, right, still there is a bulk modulus in the liquid that allows P wave to travel through it, okay, because P wave velocity depend also on the bulk modulus. Due to this reason, P wave is able to travel through the liquids, whereas as the velocity formula of secondary waves is only having the rigidity modulus, that is velocity is equal to square root of rigidity modulus divided by the density. Due to this reason, S waves are not able to travel through the liquids. So, X waves or S waves are not detected, it cannot actually pass through, right. So, if there are liquids, S waves, though you energize the ground, though you generate shocks, S waves cannot be detected, it is not able to move through the liquids. So, it is interesting, isn't it? So, this is actually helping us. So, seismic methods help us to differentiate between whether the rocks are solid or is it melting. Hope you can recollect during the initial lectures, I had given you an example of rising magma, right. This is the rock surface, somewhere here the rocks are, this region is well known to us. Here the rocks are in solid form and the solid is slowly melting, rock is beginning to melt. So, when it begins to melt, it is called as magma, right. When it begins to melt, we can try to understand that using seismic methods. Imagine it is something like a hillock, right. You are energizing, you are transmitting some signals from here, the signals are detected on the other side. This is the source and here is the receiver. And when the rock is beginning to melt, can we receive secondary waves here? No. But before, when it is not melting, we were receiving both primary and secondary waves. Now it has become a magma, rock is melting. When it begins to magma, only primary waves can reach here, secondary waves cannot come. On this example we had seen right at the beginning. So, this is how primary waves and secondary wave actually help us to understand about the subsurface. In fact, we have understood about the interior of the earth only from seismological evidences. That means seismologists understood the earth's interior only by studying how primary waves and secondary waves have traveled through the earth's interior when during earthquakes, right. So, we have the top few kilometers is the crust, earth's crust, right, nearly 35 kilometers. Then we have, as you can see, mantle, outer core, this is outer core, this is inner core. Right. How we are able to classify like this? Because of the seismic waves, right? When there is an earthquake here, the seismic waves travel through, and that means all the seismic waves, both surface, primary, secondary waves. What happened on the other side of the earth? There are several stations, we are looking for their arrivals, but we don't receive secondary waves. It is a secondary wave shadow zone. Secondary waves cannot go there, cannot be received there because of liquid outer core. The outer core of the earth is having liquid. So, due to which secondary waves are unable to travel through. What happens to the primary waves? Primary waves are able to reach the other side of the earth also, because primary waves can travel through liquids, as we have seen in the elastic from the elastic constants as well as in the velocity formula. So, the velocity formula of primary wave depend on both bulk modulus and shear modulus, whereas velocity of secondary wave depend only on shear modulus. Liquid do not have shear modulus. So, due to which secondary waves are not reaching the other side. Whereas in this case, here too there is a small narrow zone from 103 to 150 degrees. Here primary waves are not able to reach because of the angle at which they are meeting the discontinuity between the mantle and core, right. That is why there is a small gap, right, or a shadow zone where we do not receive. So, from this only the differences in the velocity of primary waves and secondary waves, we have understood what is crest, what is mantle, outer core is probably in the form of a liquid, inner core is solid. All these things we are able to come out from the velocity of seismic waves measured, monitored during the earthquakes, right. So, this is how we could understand different zones below the surface of the earth, right. What is the crust thickness in continents? In continents it is about 35 kilometers. In oceans it may vary from 20, right, 20 to 25 kilometers. Then you have upper mantle, right. This is how we can differentiate lower mantle. Then at around 3100 kilometers, we have the discontinuity between the outer core and the inner core. So, outer core is likely to be in the form of a liquid, rocks or molten. Due to this reason, the secondary waves are not able to pass through this outer core, right. We had also seen under magnetic methods, Earth's magnetism is because of differential rotation of the inner core with respect to outer core, that is likely to generate the Earth's magnetism. We had seen this briefly under magnetic methods, right. Now, let us go into the exploration part. So, why seismic methods are important? Because of the fact, right, if you look at the velocity of primary waves in different materials, right. Please have a look at the velocity of primary waves in sand from anywhere between 0.2 kilometer to 1 kilometer per second. So, please remember this is the unit, kilometer per second, right. So, in the case of sand, same sand but filled with water, velocity rapidly increased, almost it has become 2 times. In the case of dry sand, maximum velocity is 1 kilometer per second. In the case of water saturated sand, the velocity is 2 kilometers, right. Similarly, for clay, then glacial till. It is glacial till is a deposit brought out by the work of glaciers. Permafrost. Permafrost is a permanently frozen groundwater. That means beneath the surface we have groundwater. If the groundwater is also frozen, right, in regions where the atmospheric temperature is below minus throughout the year, over there groundwater also will be frozen. When groundwater is frozen, velocity of such a formation will be very, very high. Right? Velocity of seismic waves through such formations will be very high. Now, let us have a look into sedimentary rocks. First is the sandstones. So, velocity of the sandstone will go from 2 to 4.5 kilometer per second, right. And if the rock is quartzite, then the velocity is very high. Now, let us look into carbonate sedimentary rocks, that is limestones. Limestones velocity can vary from 2 to nearly 5.5. Then dolomites velocity can be very high, 6 to 6.5 kilometer. Then salt, in salt deposits velocity is high. These are the velocities for other deposits. Now, let us look into massive rocks. In massive rocks, velocity can be very, very high. It can go up to even 8 to 9 kilometer per second. Right. Now, if you have a look at the velocities of massive rocks of this with respect to the table on the left hand side, it is evident that the velocity of seismic waves is much higher in the case of igneous rocks, isn't it? As you see here, in the case of igneous and metamorphic rock, velocity is anywhere between 5 to 8.5 kilometers, whereas here everywhere it is, our maximum is 6, exception, right, only in the case of dolomites. Apart from that, the average velocity in sedimentary rocks is going to be around 3 to 4 kilometers. So, this is what we are going to make use of in seismic. So, these velocity differences can be picked up or will help us to identify what is the nature or type of rock when we conduct the seismic survey right. Then these are the velocities for other objects, right. What is the velocity in air? Air velocity is very less, right. Velocity in water, velocity in ice, oil and man-made objects, right. So, from this table we can understand the velocity of seismic waves vary in different formations. In fact, that is going to help us to understand about the subsurface by seismic methods. So, in this lecture, we had very briefly looked into some basic aspects of seismic methods, right. We said seismic waves are nothing but acoustic waves or shock waves usually generated during earthquakes, which are going to be sensed by us, and the way in which the seismic waves travel through the formation. In other words, as you see in this table, they travel with the different velocities in the formations. So, the velocity is dependent on elastic constants. So, we had a look into 4 important elastic constants. Then we had also seen what are the different types of seismic waves, and toward the end we have seen how seismic waves velocity vary in different formations. Thank you.